We are Lehigh University Space Initiative, a student-led engineering design team with over 30 active members split across 5 subteams. This year, we are excited to present the most capable rover we have ever built, thanks to significant strides in driveline maneuverability and robotic arm capability.
Our new chassis design allows for robotic arms, science, and autonomous to exist as separate modules that seamlessly connect to the chassis core. This modular system gives ample room in the core chassis for electronics and the battery, which are mounted on 3D press. The chassis is held through a differential bar connecting to each side of the spring-supported rocker bogie suspension, keeping our 6 wheels continuously in contact with the ground over rocky and hilly terrain. This new suspension is primarily built with aluminum and is able to withstand high-impact situations. We use Rev Robotics Neo 1.1 brushless DC motors to power our driveline and allow our rover to climb high-grade slopes and make turns with tank-style turning. This year's rover is far more robust than last year, with a high degree of control, maneuverability, and strength while driving.
To power a rover, we are utilizing a 12-volt, 100-amp-hour lithium iron phosphate battery, ensuring long-lasting operation during missions. Our battery has been integrated into our core chassis and laid out strategically to maximize space for wiring components and simplifying troubleshooting. To accommodate our smaller core chassis, the 12-volt power distribution board is centered inside to minimize the distance between our components. Additionally, an electronics rack is used to organize networking and computing components while keeping them accessible. Our main computer is an NVIDIA Jetson Orin Nano, providing a powerful GPU in a small package to enable sophisticated control. The Jetson interfaces with Raspberry Pis in our communication system via Ethernet, enabling the ability to interface with our driveline motor controllers via a CAN bus. Most importantly, to protect operators and electronics, our emergency stop button is readily accessible, and a 120 amp circuit breaker is placed in series with the battery.
This year, we will roll our entire C++ software stack from ROS 1 to ROS 2, containerized with Docker. These improvements allow us to integrate external libraries more easily and test components quickly without being restricted to specific operating system versions. This year, we also implemented an automated system that synchronizes Docker boots and efficiently deploys software to all computers. This makes sure all computers are running the correct software version. Additionally, we introduced a continuous integration system to manage software complexity and iterate faster. Our autonomous system integrates GPS, camera, and LiDAR data. Using this data, we can travel to coordinates as well as detect and locate posts. Last year, we introduced a unique capability called Lucid Vision, which allows us to control the rover with a 180-degree stereoscopic 3D video feed streamed to an Apple Vision Pro. This year, we can now control the arm in Lucid Vision with a 6 degree of freedom velocity control through Space Mouse, which gives the operator depth perception while operating the arm.
This year, we emphasize keeping the arm light and spec motors with large torque margins to ensure we are able to lift objects with ease. Our focus on simplicity, strength, and lightness resulted in our best arm yet. From the bottom up, our base, shoulder, and elbow joints use Neo 1.1 motors, and our wrist joints use small Neo 550s to give us precise maneuvering with 6 degrees of freedom. Our wiring and harnessing ensures that we have a large range of motion while delivering enough power to maintain high torques under heavy load. We added velocity control to our inverse kinematics, giving us fluid and precise movement. Velocity control combined with stereoscopic vision on the end effector provides the user more awareness and immersion while controlling the arm. Because of our increased precision, maneuverability, and high strength-to-weight ratio, we are confident that our arm can excel while being easy to transport and control.
Our science module uses a variety of specialized subsystems to analyze soil sites, collect a soil sample, and perform experiments to determine its potential to support microbial life. We use a variety of cameras and specialized software to gather important geographic data about each site. We use a Neo 550 motor to raise and lower a soil collection platform, which collects a sample using an auger. To ensure soil below 10 centimeters of depth is stored, a rotatable bridge discards unwanted soil. Our onboard chemical experiment detects the presence of catalase, a strong indicator for the presence of microbial life. Using cobalt-2 bicarbonate as an indicator, a custom spectrophotometer, and lab-developed calibration curves, our experiments will create a strong hypothesis about the presence of life.
Thanks to this year's significant advancements and increased system testing, we are confident in our ability to excel at this year's URC competition. Thank you. See you in Utah.